My name is David Butman. I'm an assistant faculty here in School of Environment and Forest Sciences, but I'm also a joint faculty in Civil and Environmental Engineering, which is why I'm the lucky one, probably, to get to introduce Jessica Lundquist here, who hails from environmental engineering. We're lucky to have her today, and it's going to be a topic matter that I think adds some variety to the SEFS seminar series, focusing on some water, some snow. But let me introduce Jessica. So Jessica is the Sylvester Endowed Professor in Civil and Environmental Engineering. She's been here since 2006, and her background is kind of varied. She did her master's and PhD in oceanography, but as far as I understand, didn't really spend too much time on boats and was more or less kind of looking up.
I went on several cruises. Yeah.
Did? All right. So she has spent some time on boats. But anyway, the focus of her work really involved focusing in on hydrology and snow hydrology. And she runs a really kind of specialized program here at the University of Washington focusing on snow hydrology, and also includes teaching literally in the field in Colorado. She's developed a whole course, an intensive course, learning about how to measure snow, monitor snow, and follow the water in snow and its importance for the movement of sediment and as a water resource heading downstream to the coast. And we'll probably learn a little bit about that today.
We're going to meteorology.
And meteorology as well. Right? All right, so with that, I'm going to turn it over to Jessica, and let's thank her.
Thank you very much. Thank you so much for having me, and thank you for the nice introduction, David. And today we're actually going to take a step back. It's going to be about snow, but it's about something you have to understand before you can even get to the snow. And you have to have an idea about mountain meteorology. And step number one is, how cold is it in the mountains? So, here's snow, so you have the iconic picture of Mount Rainier that I take every time I fly by, but a lot of them now. And Utah boasts the greatest snow on Earth, but if anybody says that to you, you turn right around and say that the Pacific Northwest has the record for the most snow on Earth. So this was in winter 98-99 when it snowed so much. This is Mount Baker. They had to close the mountain for 2 days to dig out the chairlifts. And by the end of the winter, they had 1,140 inches. That's 29 meters, 95 feet, or 19 Jessicas. So that's a lot of snow. Okay, so snow is important to stream flow forecasting. Out here, that lot of snow translates to about 50 to 85% of the annual runoff for all of our rivers. Snow isn't always fun. We haven't had days like this recently. This was December 2008 when everybody parked their car on I-5 and walked home. We have a whole team of people over the passes dedicated as snow fighters to keeping it off the roads so that we can keep our shipping going through I-90. But whether you love or hate our snow, you've probably heard some rumors that the snow's in trouble, right? They're the Talbot Hobbs of the snowmen prophets of doom. So this is, 2009. They changed this periodically, but the story hasn't changed much, right? We're not sure what precipitation is doing. It might be going up or going down, but most climate models agree that temperatures are getting warmer. So to understand what that means, if temperatures are getting warmer, you first have to think just a little bit about the seasonal rhythms we have in precipitation and stream flow. So how many people have lived for an entire year in the Pacific Northwest? Pretty much everybody. So you'll notice that, like right now, this morning it's pouring rain, last night it's pouring rain. We're in the wet season right now. Those of you who've lived here a whole year know that in the summer we make up for it, right? It's really dry in summer, really wet in the winter. So this is our precipitation. Now if you look at streams around the state, you can see over here that this is the Snoqualmie shot in the Olympics is a rain-dominated stream. So the time we get the rain is the time we get the runoff. You can see a mixed basin. Here's the Puyallup draining off Mount Rainier. You can see that some of the runoffs coming from the rain, some of the runoffs coming from the snow. And you can see as you go further north, you've got most of the runoff coming from the snow, right? This is the time it's raining. That's when your snow is melting. And so these shifts in the hydrograph are really shifts between rain and snow, and that controls our hydrology. So this is a slide from Alan Hamlet, who used to be a professor in our department, is now at the University of Notre Dame. And he was modeling the Skagit River. And so he said, oh, here's the Skagit River that right now, has most of its runoff when snow melts in the spring. And his model forecasted that as things got warmer, it was going to shift, right? More would come in the rain, more would have in the snow. So basically that means more floods, less hydropower, and irrigation. But Alan had some problems with this model. I'm going to tell you a little bit of the story of what's going on with this model he was running at that time. Before I get that, I just want to make sure that everybody's on the same page, because I know people have a lot of different backgrounds here. So you're getting very brief snow hydrology 101. So mass balance, snow equals frozen precipitation minus sublimation. Pacific Northwest, that's almost nothing. Pacific Northwest, 0 minus melt. Right? So it's a pretty easy equation. So the number one thing we have to figure out is the precipitation. Number one, how much? Not the trivial thing to do. That's another talk. Number two, is it liquid or frozen? Right? Those are the shifts I'm showing you in all those hydrographs. Is do we have liquid or frozen precipitation? In other words, when I got here, I was surprised that the National Weather Service had graphics like this. When you look up what's the weather going to be like tomorrow, you're like, what on earth does that mean, right? It's wintry mix. Which I've learned is the worst conditions to bike in ever. The snow and rain are both better. Wintry mix is not fun. But we get a lot of that in the Pacific Northwest. And that's one of the most important things we can do in our stream flow forecasting and snow modeling. So here are some graphics put together by Mark Rowley. So here's your typical storm. Here's your snow line. We've got snowfall up there. We've got rainfall down there. The area where you have rainfall is the area contributing to overland runoff to the stream. Up above is where there's no runoff production. That's where the snow is saving it for later in the season. You get a warmer storm. This is just a week later. Here comes a warmer storm. Now you've got a new snow line. Snow up there, rain down there. And now you have the warmer storm is producing a much larger area contributing overland runoff to the stream. So this is the dominant factor that gives you bigger floods in a warmer storm. You just have a much higher snow line, and predicting where that snow line is a big important part of predicting it. So here is just a picture from January 2009 showing I-90 when big problems happen when it rains where it usually snows. You often hear rain on snow flood. The biggest problem is it's raining where it normally snows. This is, again, looking downstream, and here's a bridge almost underwater in Snoqualmie, Washington, from those rain on snow floods. Okay, so we need to know rain versus snow. How do we do that? That depends on temperature. So basically what you're looking at here is, this is a graphic from a manual put together by the U.S. Army Corps of Engineers in 1956. They basically had people sitting out in the mountains of California writing down exactly what temperature it was and what kind of precipitation they observed for years. They compiled it all in this. And basically what you can see, this is percent snowfall from 0 to 100. Over here is percent rainfall from 0 to 100. And this is air temperature in degrees Celsius. You can see that below 0 degrees, it's all snow. Above 3 degrees, it's all rain. And right in between 0 and 3 is that really wonderful wintry mix. Here showing our wintry mix. So, where exactly is that in our mountains, and where does the wintry mix matter for our own water supply? So here we are in Seattle. Here's the Cedar River Municipal Watershed, and this is broken up into elevations. This graphic was put together by Jenna Forsyth, who was a student here a while back. And so temperature varies from storm to storm. So to know where the wintry mix is, we need to really think about a distribution. So this is frequency of occurrence. It's basically a histogram here. And this is the elevation in kilometers where the 0 degree sea level was as observed by the Quileute sounding data. So basically a sounding is a weather balloon out on the Olympic coast. They launch it twice a day, goes up with the temperature, and pressure sensor tells you how high it is, exactly what elevation is 0 all the time. So you can see that, and this is for winter months, the median value is about 1,200 meters. That's where the 0 degree sea line is. So basically in terms of the Cedar River watershed, that's our watershed, So right here on the bottom, you can see the fraction of the total area contributing to runoff as a function of elevation. So basically, if you go high enough, 100% of the basin contributes. If you're lower, smaller percentage. And here is the median 3 degrees sea level. Here's the median 0 degrees sea level. And so what you can see here is that 10% on average, 10% is really snow, 50% is wintry mix. Most of the snow in the Cedar River is actually really wet, thick, heavy, nasty snow. And about 40% is rain contributing to our winter runoff. The reason I show this whole distribution is because you have to remember that we still have days when it's snowing in Seattle, and we still have days where it's raining over the entire watershed, even up at Snoqualmie Pass. So if we think about, okay, we just warm the world a little bit, then we can shift this whole distribution up. So that means that the highest 25% of the Cedar River is going to get a wintry mix, and 75% is going to typically contribute to winter runoff. They have a small reservoir, and so they're concerned about the snow line moving up there. And then you can look this up and see that, this is, the Cedar River is right here in what's called a transitional basin, which is likely to lose the snow if it warms too much. Okay, so as long as we know the temperature in the mountains, we can predict whether we got our precipitation as rain versus snow or as some wintry mix that is neither of the above. Now back to those model simulations that I showed you that Alan was doing. Okay, so he's using high elevation temperatures and he's using precipitation estimates. And here are the observations. This is the Snoqualmie River in western Washington. The observations in blue, and Alan runs his simulation and he gets the black line. So any idea, what do you think is wrong with Alan's model?
Predicting too much snow.
Yeah, so he's got too much snow. So that's right, he's got too much snow. He's got not enough rain running off in the winter. What might be a problem? What might lead to that? Temperature. Is this model too hot or too cold?
Too cold.
Too cold. This model might be too cold, right? It's got too much snow. The real world is more winter weighting. The model just seems too cold. Okay, so what can we do? How can we investigate this hypothesis? So when we think about modeling temperature in the mountains, again, our area contributing to runoff through either having rain or melting snow depends on how temperature decreases with altitude. That's called the lapse rate. And the average decrease globally is 6.5 degrees C per kilometer, which means that, if right here it's 15 degrees C, this average temperature at sea level, just decreases on average up here. And right here where that intersects 0 degrees C is where we, draw our nominal snow line on the mountain. We're going to get wintry mix below that. Okay. But the reality is that this lapse rate could range from 3 to 9.8 degrees C per kilometer. And you can see here that that range changes where that 0 degree C line intersects the mountain by quite a bit. All right, so this is a graphic courtesy of Phil Mote, who used to be the state climatologist here, has now moved to Oregon. And he was looking and saying, okay, well, if you want to know the lapse rate, you want to know it over a long time, you probably want a really long-term climate station. And so he pulled this up and said, what this is this is elevation, and this is year. And the line is when there was good data at a station, and then all these words are just the names of the stations. And really, if you wanted something that was up there for quite a while, the longest term stations at higher elevation, I mean there's a lot down in Seattle, were Paradise at Mount Rainier, and then our mountain passes. So Stevens Pass, Stampede Pass, and Snoqualmie Pass all had fairly long records. So another piece of information you need for this puzzle. In the winter, there's often cold continental air trapped just east of the Cascades. How many people have flown out of Seattle and seen something that looks kind of like this? This is another one of my pictures out the airplane window, right? Here's Mount Rainier, east side is colder, west side is warmer. And that is a common wintertime occurrence. the cold air often penetrates westward via the mountain passes. So you can, again, see just by the clouds track, the cold air in this case, going in snow-plowing paths. And this was written up in a very nice paper led by Jim Steenberg in 1997. Jim Steenberg's the one who coined that Utah had the best snow on Earth. He left us with Utah. But he was really into hanging out to the ski resorts, and his point was that the Cascade Passes, the reason we have Snoqualmie and Stevens ski resorts in the passes, and that they can be there, is because they actually have cooler winter temperatures and more snow than other similar elevations. So here's from Jim Steenberg's paper, and you can see that Paradise, which is at about 1680 meters, is actually in the winter 2 degrees C warmer than Stampede Pass. Stampede Pass is right by Snoqualmie Pass on I-90 at about 1,200 meters due to that effect. Okay, so when Alan was having this problem, he talked to Dennis Lentenmeyer, who's a former professor here, who's now left us and went to UCLA, and he assigned his class, a whole group of civil engineering students. He said, you guys need to check the lapse rates used in the hydrologic model. So what they did was they selected pairs of one low elevation site and one high elevation site, and they were really careful to make sure they only got sites with really long-term records. Then they fit line to determine the average decrease in temperature with elevation. So remember, only a few high elevation sites were available. So here is, this is actually the day of taking pictures out my airplane window. Turned out Modus also took a nice image here on January 2009. And you can see here's Paradise on Mount Rainier, here's Stampede Pass, Snoqualmie Pass, and Stevens Pass. And these are the only ones with really long records. So they grabbed these. However, the one at Paradise looked like an outlier. It looked like it was doing something different from the other three, so they decided to throw that one out. So this, I'm going to take the same picture. This is visible image. Now I'm going to look at this in a false color, including non-visible wavelengths, to really highlight where those low clouds are. What you see is the problem with this picture and with what the students did.
East flow. East flow of clouds.
That's highlighting the mountain passes, right? Where you see these low clouds, right, the mountain passes. All the stations they kept were right there in the mountain passes that tend to get cold from that easterly flow. And zoom in, again, here's just looking at where the stations were: Stampede, Snoqualmie, Stevens Pass, Paradise, Mount Rainier. Okay, and they calculated the lapse rate, and they found that on average, temperature decreased about 6.5 degrees Celsius per kilometer. That matched the global average, and they were very happy. They solved their problem. Except that was the lapse rate they were already using in the model. And the model was too cold. So what can we do? Stampede Pass in the winter is about 500 meters lower, but 200 degrees cooler than Paradise, what was in Jim Steenberg's paper. So if maybe the true lapse rate actually is different, right? Maybe even though 3 of our 4 looked like that was right, we have a biased sample. Maybe it should be this, right? That would change where you put that 0 degree level on the mountain quite a bit. Extrapolating these lines up. So how can we check? So the idea was, how do you adequately map temperature across complex topography? Key is, you really need a lot of sensors. Only having weather stations in mountain passes doesn't actually sample the mountains that snow is falling on in general. And so you need a lot of sensors. This is a view from Maple Leaf Pass, North Cascades National Park. It's right where the road, Highway 20, goes across the hike up to the top there. So we got a whole bunch of, if you need a lot of sensors, you want cheap ones. So, having the Pacific Northwest salmon industry, these people now use them as like ID fobs on cars too. But we use these temperature sensors, the Dell Semiconductor eye buttons. They only have about 0.5 degree C resolution, but they can sample once per hour, fill up with 11 months of data. cheap, mass-produced because they're for checking that your salmon didn't become unfrozen in transit. And so we decided to put them out all over the mountains. Now, remember, to measure air temperature, the sensor must remain above the snowpack, which can be up to 40 feet deep in the Pacific Northwest. So you can climb the trees. This is Jeremy Littell, who was in town here, has now moved to Alaska, where the trees aren't quite so long. Or you can just launch the sensors into trees. That's me with the Hyperdog tennis ball launcher, because I was not as good at climbing trees as Jeremy. It actually worked. We put these all over North Cascades National Park and retrieved 100% of the sensors from trees all over successfully back in 2008. Here's just a picture of where in the North Cascades they all are. Again, you see, by necessity, we put out a lot of these, but they are along the road. That's where people can get. There are a couple cases where we hiked on trails out the road. We'll get back to that, and you can see, this is the pulley system with the temperature sensors way up there in the tree. Okay, so what do you get? So now, we only had 1 year. We didn't have a long-term record, but we had a lot of sites. So if you take all the sites and do the average temperature over the year versus elevation in meters, you get 4.7 degrees C per kilometer, or about 5. So standard lapse rate, 6.5 degrees C per kilometer, would predict the higher elevations are considerably colder than they really are, according to this. So, that's 1 year, and the other were long-term records, right? So how do you balance the trade-off between long time series of records versus lots of spatial coverage in records? So Justin Minder put together a paper that was published in 2010 that tried to really get at that, of like, what is the answer? And so here's my North Cascades eye buttons I was just showing you. They're up there. And roughly, 5 degrees C per kilometer. They were only for 1 year. So here are longer term. These are 06, 07. This is 07, 08. And it turned out that weather balloon data didn't matter whether you looked at the long-term record or you looked at just 1 year. Also had an average of -5 degrees Celsius per kilometer. Turned out that a mesoscale model, this was the one run by Cliff Mass's group for weather prediction. At that point it was MM5, it's now been updated with WARF. The model said it was 5 degrees Celsius per kilometer. And cooperative observing stations, which included those long-term stations, plus some that weren't quite so long. And this is a period from 1949 to 78, because if you remember all those lines, that was the longest set of continuous records. A lot of them were discontinued in 78. They and cooperative observers are people, they go out and they write down the minimum and the maximum temperature each day. So we calculated that. The minimum had a slope of 4 degrees C per kilometer. The maximum had a slope of 6 degrees C per kilometer. You took the average of the two. The average temperature had a slope of 5. So it doesn't really matter how you look at it. It's about 5 for the whole Pacific Northwest, not 6.5. Okay, so this could explain the difficulty with those stream flow simulations. The model's too cold, too much snow. You change it with a different lapse rate. Okay, however, before we declare victory and say we figured out what's going on, we got the right lapse rate, we fixed the line of the model. Something else I wanted to show you with those long-term stations by Mount Rainier. Let's look at that one more time. So if you notice again, here's the graph of just when you have data anywhere in the mountains. The two longest term stations are Paradise and Longmire in Mount Rainier National Park. And so if we just look for high elevation, if we just look at the two of them, what's the lapse rate there? By month, this is what we get. So this is over 1978-2000. This is the average monthly temperatures at Longmire, which is at 840 meters elevation, and at Paradise at 650 elevation. And then for each month, I've calculated, based on those average temperatures, the lapse rate. So here's over 20 years. So let's put this in context with what else we've been talking about. So here, 6.5, that's the standard lapse rate, and that's the amount based on the mountain passes, right? So it's generally lower than that, with the exception of in June. Here was the lapse rate calculated from the data in the North Cascades, and 5 was about the number that came out from most data sources. You could drab in any way, shape, or form, which kind of does go through the middle of this. But you see there's quite the seasonal variability here. In particularly, the winter lapse rate near Mount Rainier is quite shallow, right? It's down to about 3, which is half of what's going on there. So how can we explain this? So you spend a lot of time hiking around Mount Rainier, and it starts to kind of gel in your head, right? If you average a lot of days like this, it's cooler down here, it's warmer up here, right? It's sunny at the top of Mount Rainier. We see it peeking out from the clouds a lot of the time. With a lot of days that look like this, right? You probably also been, if you go hiking Mount Rainier a lot, where it's warmer down here and cooler, and just the top of Mount Rainier is sitting in a cloud, right? What kind of lapse rate do you actually get, and what should you be putting in your model? So what we've been talking about so far with the lapse rate to Stampede Pass and Paradise is assuming that our base station is unbiased, right? We talked about those high elevation mountain pass stations could have cold air coming from the east and be biased cold. But what about our low elevation station? So Longmire is often under an inversion and in a cold air pool. How many people have been in Seattle in a day in the winter and you drove up the mountains and you sort of got up into the sun and it was actually a lot warmer in the mountains than it was down in Seattle? Anybody? Yeah? You've done that, right? So cold elevations can be stuck in an inversion, and Longmire is actually prone to inversions, meaning it's in a cold air pool, is locally cold, which then means that you get a lapse rate on average that decreases less with elevation. And that's going to give you an estimate of a higher melting level. So you've got to be careful not only of your high elevation stations, but also of biases in your lower elevation stations as well. So inversions occur anywhere the surface temperatures are colder than the air above. Mount Rainier and the sun in the winter is kind of a classic out here fun window example. So to interpret our station data and know what it means, it would be pretty helpful to know which stations are likely to be in inversions. Fortunately, we actually understand enough mountain meteorology that we can predict this. So we know how mountain winds work, and we can map where cold air collects on the landscape. And so I'm going to give you an example. This is a picture from Lockvale in Rocky Mountain National Park, Colorado, where I also hike to put out temperature sensors. And if you're kind of detecting where I put them out, places that are really good to go hiking, right? All the national parks have temperature sensors. And so basically the physics are, how do you get an inversion? So at night, everything emits, all the time everything emits long wave radiation, but at night things aren't going up from the sun, right? So long wave radiation cools the surface. So the air right next to the surface is the coldest. Cold air is denser than warm air, and so the cold air flows downhill, down valley. Therefore, the cold air can collect in flat valley bottoms and local depressions. And in particular, it will collect somewhere in a valley that kind of pinches in at the end where the air can't keep flowing down. It will get trapped, often places that are quite flat and constrained valleys, often near lakes. So we can map and model this just using features on a digital elevation model. So here is, that's what I just was showing you pictures of. This is elevation contours of Lockvale Watershed and Rocky Mountain National Park. This is a map of slope. So we're looking at places for a flat slope. This is a map of curvature. We're looking for places that are concave, right, where the air is going to get trapped. And then we're looking for places that are local depression, right, which means the surrounding part is higher than where you are. So we put these together as fields. We can actually just predict the probability of that place on the landscape being prone to cold air pools. And so right here, in between, which means sometimes it's known as gray, cold air pools are white, and no cold air pools are black. And you can see that places that had a flat slope, concave, and local depression show up as white here. And what may be harder to see from the bag is that these little arrows are where, with the temperature sensors, we could validate that that was true on the landscape. Okay, so we know how to do this, so let's run the algorithm over Mount Rainier. So here's the summit of Mount Rainier. Here is Paradise, and here's Longmire. It turns out Longmire is in a cold air pool, and that's part of what we were seeing in the data at Mount Rainier with that really weak lapse rate. All right, how about our data at North Cascades? So if we're trying to understand how topography relates, something you got to think about with any temperature sensor anywhere, even when you put out 20, is, just for practical reasons, most of the sensors were along roads or trails, which follow the valleys, right? But here's the topography in colors, and most things were along the road. Okay, so here if we run the algorithm, even though we deployed 25 sites, most of them were in cold air pool locations. These, along Maple Leaf Pass, are the only ones that clearly weren't. So here's a picture, and this was a hiking trail I just wanted to go on. So we just hiked up here and did a transect going up to the top of the ridge of temperature sensors. And what you can see right here, here is the day, November 23rd, 2007, very prone to cold air pooling. And these are the sites in Maple Leaf Pass. Despite being the highest elevation sites in the entire study, they are the only ones that are above freezing during that day. So in this case, the inversion is so strong that you would actually get a lapse rate going the other direction. All right, so mountain temperatures and consequently snow vary with the frequency and intensity of these inversions. This can lead to quite variable trends in different locations. So remember we talked about sort of the climate question in the beginning, temperatures are warming, what's going on? There have been a lot of debate about are mountains warming faster or slower than the lowlands? And so this was a paper that I worked on with Nick Pepin, where we tried to find, again, they're very hard to find, any long-term mountain temperature site we could that had been reasonably well maintained. And we wanted to know, what was the temperature trend in degrees Celsius per decade? So mountain summit sites, right, are not in a cold air pool. They're up quite high. And you can see that, most of them, this is the global mean trend, is right here. And here, this blue line is 0 degrees C, no trend whatsoever. And you can see there's not much trend. There's definitely no evidence that mountain summit sites for this period were warming faster than the lowlands. However, if you look at mountain valley sites, it looks like a shotgun blast. Some of them are warming much faster, some of them were not warming as fast. And a lot of this could be due to just changing frequency and intensity of those inversions. We know that all the valley sites are prone to inversions, but what we don't know is how frequently they get those inversions and how cold they get under those inversions. And if you just change the weather patterns so they could get colder, some of them are actually getting colder with time due to weather patterns while the rest of the world on average is warming. So where are we going with this? So you saw that had this great plan of going hiking in all the national parks, putting out temperature sensors. And he had 2 kids and they were really hard to take hiking and put out the temperature sensors. So now what do you have to do if you have 2 kids? You need satellites to help you. So that's why moms become space scientists. So now we're doing lapse rates and cold air pools from remotely sensed thermal IR. This is a field study we did in Colony Meadows with an airplane. There's multiple satellites that give you the same information. You can actually see the temperature of the trees and the snow. You can separate the temperature of what's the snow and the trees. And then you can map out, it turns out that tree temperature matches air temperature pretty closely. And by mapping the temperature of trees with elevation, you can get the lapse rate of the purple. We haven't done it yet, but that's the next best thing. Okay, so a lot of these variations I just showed you are actually pretty small. And sometimes they seem small, like something only a pika living in a cold air pool would care about. And I actually bring that up because when I published my work on cold air pools, I thought that all the hydrologists would be super excited about it. Turned out that only, people who are studying pikas absolutely love pikas live in cold air pools. There were a lot of other ecological implications that people studied. There's papers on cold refugia, right? These are those valleys that stay cold when everything else warms. But they really, beyond that, do affect distributions of rain and snow, melt rates, and how we understand and model them. So again, here are these 2 lines. They could represent a number of things. Here's our current stream flow. Here's our expected flow with warming. Similarly, these two lines could represent a model simulation with a 6.5 degrees C per kilometer lapse rate versus a model simulation with a 5 degrees C per kilometer lapse rate. It's the same degree of difference for our areas, so it is an important parameter to get right. Average over a large enough area, a lot of these local effects will average out, right? You have mountain passes, which are 6.5 degrees C per kilometer, Paradise Longmire showing a 3.5 degrees C per kilometer, and the truth on average is somewhere in between. Here's our average, right? However, if you make regional assumptions based on only a few stations, you can be very, very wrong. It's dangerous to grab just a few stations and decide they represent the regional average. I want everybody to know that if you are using a gridded data set for anything you are doing, beware, because this history is in these data sets. The NLDAS data set, the Maurer et al. Data set, and the Livna et al. Data set all assume a constant 6.5 degrees C per kilometer lapse rate everywhere. Therefore, they're going to give you the wrong rain-snow transition in the Northwest. Prism and mesoscale model output are both better choices. The reason I'm telling you this is because I see it almost all the time. So this is a graph put together by Jeff Keck, who's a current grad student in the department, conversation yesterday. He was trying to simulate November 2006 flood event in the Skagit water set. And he wanted to use the Livna data set. Remember, that's the one that's gridded with a 6.5 degrees C lapse rate. He's showing just a trace of daily minimum temperature from that data set, as well as from 2 data sets from mesoscale models. And you can see that the mesoscale model data set, this atmospheric weather forecasting type models, are in the red and the yellow. The Livna data set's in the green. And you can see it's for this region where this watershed is, it's 5 degrees Celsius colder over this period. And what that actually does, the red one also has the most water, that's precipitation coming out. What you can see in terms of stream flow, getting the flood. So here is the black line of the flood. He's trying to simulate his flood and sediment studies. The green line down here is what he gets for the flood using the Livna data set. It has actually about the same amount of water as the Solitaire data set, but because it's too cold, this is all snow and you don't get the flood. So you get all your dynamics wrong just from choosing the wrong data set due to these students at UW 10 years ago who picked the mountain pass stations and threw out Paradise. So, in conclusion, I would like to thank all the people who helped me. There were a lot of graphics and inputs put together by the Climate Impacts Group of 2009 here. Justin Minder did freezing level analysis. He was a graduate student here, is now a professor at Albany. Andre Sherbina took all of the Pica photographs and other great photographs. Mountain Hydrology Research Group through all time, as well as all of the people who helped with I-button deployment and with temperature, cold air pool analysis, as well as Steve Burgess and the Seattle Times photographers who give you pictures of floods, funding from the Park Service, the National Science Foundation. And I left plenty of time in case you have questions. And if you ask me hard questions, I'll say your snow sharp.
I know you mostly focus on mountains around the Pacific Northwest, but just like in general, obviously I'm sure that you've researched throughout the nation, maybe around the world. How do you consider latitude into the temperature of these findings? Or is it just somewhat negligible when you're comparing to...
In terms of the lapse rate?
Yeah, just like, well, that and just like general temperature, because I'm sure like the change in the curve of that has to be different in mountains that are maybe just higher up latitude-wise, or...
So latitude's a good question, but latitude actually isn't the right parameter. So basically the global average is 6.5 degrees C per kilometer, right? So by virtue of that, you should know that, clearly some things actually have a steeper lapse rate than 6.5 degrees C per kilometer. Some things have a less steep lapse rate. Pacific Northwest has a less steep lapse rate. The reason is because of how moist we are. So actually, the steepest you can get is 9.8 degrees C per kilometer, and that's called the dry adiabatic lapse rate. And so that's due to the ideal gas equation, PV equals NOT, right? If you just go take meteorology classes, that's the first assignment they'll start making you do is, okay, you've got a dry piece of air, you're gonna move it up and down, what's gonna happen, right? Just due to pressure changes, the temperature will change, and that dry air mass will cool at a rate of 9.8 degrees C per kilometer. So basically, if you go to drier regions, you get steeper lapse rates. The Pacific Northwest is a very moist region, and it's pretty moist here most of the time, particularly in the winter. That's what you saw, that some of our steeper lapse rates were actually in the summer from that mountain you plot. That's when it actually gets drier here and we have steeper lapse rates. And because we are so moist most of the time, we actually are cooling at what's called the moist adiabatic lapse rate. And so actually the air is cooling and condensing, and that then keeps the air from kind of temperature-wise cooling at quite the same rate. So you want to do it by moisture. Latitude may or may not be correlated with moisture.
Yeah.
So I have a question about storms in
Yes.
adiabatic lapse rate. Do we have data from weather balloons and storm events? I mean, one would imagine that, which what could really happen is those big storms come in, they have a much different temperature profile as it moves up in the mountains, and that might help you predict that difference in the model.
I get this. So this paper right here that Justin Minder put together in 2010. So these are all the soundings, these are by years. He has a lot more graphs in the paper. He sorted them out by storms. And so the storms on average are about 5 degrees C per kilometer. There are different storms, there's variation. So on average, the storms are that. Between storms, you can get different lapse rates. And that's the reason why we're really interested in looking at the mesoscale model output, in that an atmospheric model would dynamically simulate the physics, right? They have the gas equation, they have the moisture contents, and they do, all the math involved with lifting the parcels, and so they often will do a better job if they get the storm right, which, is iffy in some forecasts. But in general, if they're simulating it, they will get the lapse rate for that storm more accurately. It's by modeling the atmospheric physics. Yeah.
Have you found carbon emissions to be any kind of influence on these temperatures you find in the mountains at all in your research group?
And car emissions?
Like carbon emissions, like greenhouse gas, have you found that to influence any of it at all?
I mean, I think there's two different things, and let me see if I can go back to, don't send it here. No, go away. Okay, let me go back to the very, very, very beginning. This one, if I can put this up. So in terms of, these are simulations that are really taking into account carbon emissions, right? And so what carbon emissions do, it's, a greenhouse gas for the globe in general, is that we're really good at predicting in general over the whole globe, temperatures get warmer. Now the question, which, correct me if I've got it right, you're asking, will lapse rates change? Is that in terms of?
I guess kind of temperatures.
So in general, we expect everything to get warmer. The thing to keep in mind is that, the local weather is often a bigger signal than that sort of, average over the globe, right? When you average over the entire globe, yes, which that increases your probability locally of being warmer, but it doesn't increase certainty, if that makes sense. And then what I was showing you with those mountain stations is there was a lot of questions like, does that change the lapse rate? If you put more carbon emissions, do higher elevations or lower elevations warm faster, which would change the lapse rate, how temperature changes the elevation. And that's still a debated topic. There are a number of models that say it does, there are others that say it doesn't, and the observational evidence is really hard to find because those stations just haven't been there that long, and they aren't maintained very well because it's hard. Yeah.
Jessica, so you're saying the lapse rate is different because the Pacific Northwest is moist?
Yes.
So have you been able to test that with other mountain ranges? The Olympics seem real accessible, and not just the Cascades, and I don't know about other mountains in the world.
So the Olympics are pretty close to the rest of the Pacific Northwest. The Olympics are really wet. Ryan actually might know the exact lapse rate in the Olympics. He's looked at the Olympics more than I have. 4.5. 4.5. Okay, so it's less steep, moister. The Sierra Nevada is actually perfect 6.5 degrees C. Yosemite National Park, I've done a ton of work, fits 6.5 degrees C perfectly. So live in a data set right there, great. Don't use it in the Pacific Northwest. And if you go in the summer in the Colorado Rockies, so the Lockvale study, the average lapse rate for the summer there, the average was like -9. It's very dry there, particularly in the summer. And so yes, the moisture definitely is the best predictor of what lapse rate would be in general, on average. Yeah.
Just I had a question. You kind of alluded to this next phase of work using satellite imagery, thermal imagery. And the implication there is you could come up with pixel-based infinitesimal combination of lapse rates in some ways, right? And so how do you see that as moving this work forward?
Number one, I think one thing you'll notice from this is that the atmospheric models actually seem to be doing better than the gridded data sets. That gets a little bit scary because the gridded data sets are supposed to be interpolations between observations. And so how do you know? So if the atmospheric models look better than the observations, and you've got two atmospheric models that give you slightly different answers, how do you even pick what's the best atmospheric model? So I think we can actually, with the satellite data, come up with global scale evaluation data sets. So you can actually say parameter A or B are better than the atmospheric models. The thing to be aware of is they're going to be really good at cold air pools, which occur in clear sky conditions. They're not going to be very useful in terms of storms because you're just going to see the temperature of clouds. So for that, you're still going to need some UV or UV temperature sensors or something else. But it turns out that atmospheric models in general are pretty good at storms, and they're incredibly crappy at clear sky conditions. They just decouple, so they actually need more work there. So it could actually help them with the weakest. That's where I'm going. Yeah. Yes.
I have 3 questions. I studied microclimate in Rainier just after my experiments last year. So with that, we showed the Pika there because one of the sites which I was studying was below Mount Rainier, and it happens to be around 200 meters below. And it happened to be cooler than Paradise.
Yep.
So that seems to reinforce that there is no data quality issues. Is that a fair assumption? Because I think even in your colder...
We could even try to find your site if you want. I'm not right here. I don't know why. His cell is just very grumpy. So you can find Mount Rainier, you can like, see. There's Mount Rainier.
Yeah. So the sites were not 200 meters.
Are you like Reflection Lake?
Yeah, exactly.
Right there?
Yeah.
You're right. A really good cold pool.
Yeah, exactly. So that was one of my hypotheses, and I guess you gave me a good evidence that it is. Because ours was, so that was my first thing to get a confirmation. Thank you. Second was that would you see that cold air pool kind of materializing even at a very final level? Because we had sensors at 0.3 meters, 0.6, 0.9, and 1.2. All the way, if I relate to Yannicka's, which is 1.2, or 2 higher, do you think that I would see the same kind of inversion happening at that scale? Also?
Yes. So inversions and cold air pools are actually a fractal process. And I've talked to a lot of people wanting to use this code. It's actually a scale-dependent code, and you have to have the appropriate size DEM, and you have to set appropriate size scale length. This one is set up for mountain valleys, because that was what I was interested in. If you go out to a vineyard or crops, you'll actually see that people will design them for crop frost protection. You'll also see, you probably have been out like on your lawn or walking around in the morning where like frost is just starting to develop. You'll see little rivulets, and you'll see like the bottom of like little wrinkles in the ground surface will get the frost first. So it occurs on very small scales in addition to larger scales.
So following that hypothesis, would I expect like a dramatic difference between 2 meters and ground?
Yes.
Given that, okay, okay.
We should probably let someone else answer your question. You could grab me after. Yes.
Why continue to use lapse rate rather than incorporating atmospheric models? I mean, a lapse rate is a simplification, right? And you're saying we should apply a regional calculated lapse rate to the varies across the world. But it's not the true process of temperature variation on the landscape.
I mean, I think you just summarized one of the points of my talk. Why?
I mean, I asked because most of your talk is about lapse rate, but like, that's the coarsest approximation of temperature. There's much better progress now.
Absolutely. I think the truth is that like there's a lot of history in how science is done, and a lot of people say, you know, I'm not a meteorologist, I'm focusing on X, I just want something straightforward. A gridded data set looks like it's data, it's based on observations. What a lot of people I think don't realize is that in the mountains there's not a lot of data going into that gridded data set, and it's based on that one line. These data sets are used very commonly for a lot of applications and end up in a lot of very sad graduate students who can't understand like why they can't simulate their flood or their pikas are in the wrong place or whatever else, right? It takes significantly more technical skills to be able to ingest data from an atmospheric model. A lot of the atmospheric models are evolving so quickly that it's hard to, you know, you have to actually have a friend who's a meteorologist to keep you up to speed on like, no, you don't want that model anymore, you want this one. That a lot of people go back to the old school way. And in all honesty, if you just do -5 per C, you're actually okay. It's just that we, by this odd twist of history, got the wrong number for our entire state. For most applications, you actually don't need the advanced capability of a mesoscale model, even though that would be, for many applications, a better choice. Very bad.
This is sort of a forward question, but I spent a decent amount of time in the mountains, and when you look at a snow line from across the valley, it sort of sometimes has a different thickness. Like in various places, snow lines will be very crisp, and then sometimes they'll be thicker. I don't really know how else to describe it, but what are the factors that are involved in like actually determining the snow rain transition at that very small scale? And like, is that something that's variable, or am I making that up? How you determine what the line is?
You're not making it up. It's absolutely true. And there are multiple factors that go into it. I mean, this is kind of the most basic level of mountain meteorology research. Nick Wayand did a really nice paper of just forecasting rain or snow exactly at Snoqualmie Pass. Nowhere else is it rain or snow at Snoqualmie Pass. And so the things that actually change locally, what you get on one side of the mountain or the other, is that you actually, you know, the storm comes in, and the storm comes in fairly uniformly, but our storms are so in that wintry mix area that they can be influenced by what's happening underneath them quite strongly. And so, you know, at Snoqualmie Pass, the reason is that you often will have this warm storm coming in, but you have this really cold air that was there before the storm got in. And so the storm comes and it mixes with that cold air, and it keeps it just cold enough to keep the snow going longer. You sometimes will see differences on north versus south facing slopes. The ground is just warmer, right? That wintry mix too, like, is it gonna stick? Often, like if the ground's a little bit warm, it melts and it doesn't stick, right? But if the ground's cold, it will, and then if you get snow later, it sticks. And so it's a lot of the prior conditions, and there's a lot of really fine scale variability right at that transition.
You take one more question?
Yes.
I had a question about the PRISM models. You were saying, do you incorporate the variability in lapse rates? Do they do that simply just by adjusting it for moisture at the same scale? Or how does that actually work relative to the simpler ones that assume the 6.5 degrees?
Let me show you. There's one picture I think I can show you pretty well what the PRISM data set is doing here. Is actually this one is that you actually can see that the cooperative observing stations are everywhere there is a blue or a red sideways triangle. They have shorter data sets. So PRISM is actually utilizing, it's mixing in and out stations as they come in and out of the record. The reason why actually the Maurer and the limited data sets didn't do that was that they wanted a stable base. They really wanted to be, their idea was for climate simulations, you should have the long-term record, because otherwise you'll look climate fluctuations just from different stations coming in and out. And they thought that would bias their record. They inadvertently, by just the virtue of which sites were there for a long time, bias their record by only choosing long-term ones. PRISM takes everything it can get its hands on, and then does the lapse rate. And it also has like weekly varying lapse rates. It actually is a much more complicated interpolation algorithm.
So they're empirically derived as opposed to.
Yeah, so PRISM is empirically derived, but it's using more stations and it's using shorter term stations. It's also ingesting the NRCS SNOTEL station temperature records, which is a different story. They also have problems, but they help with the labs, right?
All right, if anyone else has questions, there'll be some time afterwards with some refreshments. We'll probably catch Jessica for a little bit, but why don't we thank her?